Right, so let's start straight away because we don't have time. So I'm going to kick off with potential flow today. Just to say a lot of these notes are originally prepared by Sean, but I'm changing things because everyone is different the way they want to present things. So the learning outcomes to help you recognize streamlines and velocity potentials. What do we mean by velocity potentials? Talk about circulation, a rotational flow, and hopefully, as we progress, show you how to apply the concept of velocity potential to describe flow fields. Okay, even flow field around aircraft and other complex aerospace systems. So, I thought before going any further, I'll just go do a very quick review of some of the concepts we had last year with Intro to Aero, and then we can. All right. So we spoke about ideal fluid, and we said that an ideal fluid, really, in simple terms, is a fluid which has no viscosity or no friction, frictionless. Okay. We know this does not exist in life, but obviously is an approximation, and it makes our life pretty simple. However, as long as you're aware of that approximation and that assumption, then you know what you're solving for. Okay. Another posh name for a fluid with no viscosity is inviscid. So they're obviously simpler to analyze. Okay. But as I said, bear in mind that they are limited by the assumption, the very same assumptions you're making. And we can use them as a benchmark. Now, in real life, we know that a lot of drag on an aircraft is due to the viscous drag component, particularly in cruise, right? So, if you're a genius and you come up with an idea where you reduce that viscous drag to a very low level, then you'll be, trust me, you'll be a hero in aerospace. And one way of doing that is really to play around with viscosity. Can you do something by viscosity that you make the effective viscosity as little as possible? Unfortunately, we haven't succeeded that much so far, but that's what it is. So, because ideal fluids say, I have no viscosity, so I don't care about viscous drag. In real life, can we reduce the effects of viscosity to the minimum that the viscous drag is reduced? And that's why this ideal concept is a benchmark for real fluids. We also said you can classify aerodynamic flows in many ways. So in terms of dimensions, you can have a 1D flow. That's just a flow in one dimension. For example, if you're thinking about, you can think about a flow in a nozzle, okay? For example, or the entry to an engine, okay, the intake. In many cases, it's actually most of the changes is just in one direction. So the other two directions are not important. So you can actually assume one direction flow. In other cases, that's not true. You have to consider the y as well. So you have to go 2 dimensions. And in other cases, life is actually 3D. So in other cases, 3D has to be considered. And one way to recognize that is just by the velocity field. So in one dimension, the velocity vector v, bold, this means a vector, has only one component in the x direction, which has unit vector I. In 2D, it has u and v, and of course in 3D, u, v, and w. So that's one classification, just to remind you. The other one is inviscid and viscous. I already spoke about inviscid, no viscosity or frictionless. Okay. Opposite to that, of course, is viscous flow. That's what real life is. The next one is steady versus unsteady. So steady, whenever we say the word steady, means no variation in time. So the way to think about that is there is a flow which is set, like flow over a wing. And with time, and after it settles down into a certain pattern, then with time it doesn't actually change. Again, you can see why this is a good approximation. It's just you don't need to care. Once you solve the flow, you don't need to care what happens with time. It's just a steady case. And I think a lot of you will do the steady case in your CFD labs. And that's, of course, a good way of solving the flow. Again, life is actually unsteady. Things do actually change with time. But then as an engineer, you say, well, is the change actually that much that I care about? And if you find that the changes with time, or from experience, for example, we know that the changes with time for this given problem are minute, then you just say, well, I don't care about this small change in time of the flow with time, so I'm just going to assume is more or less steady. And that's actually a good approximation. Whereas in other times, running a steady case for a given flow just gives you the wrong solution, right? So you just need to be aware of that. Uniform, so steady to do with time, uniform to do with position. So uniform, all for a given time, one parameter, let's say velocity, does not change with position. Okay, I call that uniform. And a good example we took last year is if you have a flow over an airfoil away from the body, you have the streamlines, they have the same velocity. That's called a uniform flow. Non-uniform, of course, it changes with location or position. Another one important classification is in terms of density changes. So, in certain cases which actually then links to the speed, which we express as in terms of Mach number. So, if the Mach number is typically less than 0.3, remember guys, the Mach number is the ratio of the local speed of the flow to the local speed, sound speed of the flow. So, local flow by the speed of sound gives you the Mach number. If the Mach number is less than 0.3, roughly, we say that the flow is incompressible. What that means in real life is that your density does not change. You don't need to care about density. You just say it's a constant, whatever that number is. If you go to high speed, however, trust me, the density will change. All right, the density of the air, which is now in this room 1.2, suddenly becomes maybe higher. Okay, and you need to care about that because that has real physical effects. So that's what incompressible, compressible. So you can think about it in terms of Mach number, but more fundamentally in terms of density. Oh, I forgot that one. That's just to think not changing with time. What this means here is it's only in terms of location x, y, z. We can drop the time there because it doesn't change with time. Whereas with time, for n-steady flows, you have to think about t as well. Right, streamlines. So we spoke about streamlines last year when we said that as aerodynamicists, we are always interested in understanding what the flow is doing. Okay, where is it going? How is it behaving? Okay, is there some flow rotating? Is there some flow separation? What is the flow doing? Because if we look at the picture of the flow, that tells us a lot what the physics are doing, and then you can interpret that in terms of forces and moments. So, and one way to investigate how the flow behaves or what the flow is doing is through streamlines. So, streamlines of flow, by definition, are, of course, lines of flow, but they have a very particular property, and that is at every point of the line, the tangent to that line is in the direction of the velocity vector. So the velocity vector is tangential to that line at every point, and that gives you streamline. So that's, in a way, that's a very mathematical definition. And when you look at those directions of the velocity vector, then that will give you a picture of what the fluid is doing. Now in 2D, because it's a line, if you guys remember from your maths, you can just get an equation of a line. In 2D is in terms, it basically can be written as y equal a function of x. So this is a streamline, as I said. So the velocity vector is tangent at every point at a given time instant. Okay. Now at a different time, the flow picture might change, but it's always true that the velocity vector is tangent to the line. That's the key thing. So as I said, the equation of this line can be written mathematically as y equal to fx. In 2D, of course, we have velocity vector with components u and v. And anyone remembers the equation of streamline for last year? Top of your head? No? Okay. That's the equation. So it says dy dx equal v over u. So basically the tangent, that's dy dx, equal to the ratio of the velocity component in the y direction v divided by the x component u. Okay. Now, of course, I showed you last year in a few examples where you start with this differential equation. What you want is y equal fx. So obviously you just integrate, put the dy dx on one side, and integrate, and you get an equation for y equal fx. That's the equation of streamline. Okay. Right. We also spoke about, if you remember, we spoke about vorticity, and we got even to, I told you something about potential flow, but probably you don't remember. So, how do we start? Now, we know that one of the characteristics of fluid is rotation. So, the fluid elements can actually rotate. Okay? That's one of the characteristics. We will actually show you some of the other characteristics, but one of them is rotation. And if these fluid elements, they rotate with an angular velocity omega, then based on that, we can actually define another property called vorticity. In two-dimensional, because that's what we're considering, there's only one component in 2D, that's called zeta. And this zeta is basically twice the angular velocity of the fluid elements. So it's kind of a definition on a microscopic level because you're looking at the fluid elements. So mathematically, more importantly, how do we say what is vorticity? If someone asks you what is vorticity in aerodynamics, you just say that's the vector product of the delta operator delta times the velocity vector v. Now, velocity vector, of course, is very important for us because from the velocity vector we can get the pressures. From the pressures we can get lift and drag. All right. So it's very important to relate anything, to be honest, in aerodynamics to something like the velocity vector. So mathematically, that's the definition. That's a velocity product. Okay. What can you tell me about the characteristics of zeta? Is it a scalar or is it a vector? From that definition. You guys remember your maths? What's the result of a cross product? It's a vector, yes, definitely. So vorticity is actually a vector, right? So it has magnitude and direction. Just to remind you, if you haven't seen the delta operator before, some of you have, I think you should be taking it at least in a year or two now. So it's just defined by this, the partial derivative of something by dx times the unit vector I plus the partial derivative of something by dy times j. So, of course, delta itself is a vector operator. So that's it. That's your vorticity. Okay. So it's delta times the velocity vector v. So right. So this is just the equation written again for vorticity zeta. Now, if we actually write this in 2D, actually we end up with this equation for zeta. I forgot something. I should have put times k. So otherwise, you should have tell me that should be a vector. So I'll rectify that. That should be between brackets times k. But anyway, we know in 2D we only have this component for vorticity. Now, the key thing I want you to notice there is that vorticity is now defined in something called the velocity gradient. What is the velocity gradient? Is very simply the change of speed with distance. Okay, that's the velocity gradient, and that's actually quite interesting to remember. So your vorticity, we know it comes from the velocity field, but also you can think about it as in terms of velocity gradients, how the velocity changes with distance. So all these kind of concepts are quite important to remember. Now, mathematically, also, delta times v is called the curl of the velocity field. I'm sure you've seen that in maths. And what is of interest to us is two cases. When the vorticity is 0, that means that product delta times v is 0. We call that irrotational flow, which means there is no vorticity, i.e. there is no rotation in the fluid. All the fluid elements, they might be doing other things, but the one thing they're not doing is rotating. And how do we know that? If we take the product of delta times the velocity field and it's 0, we are assured that none of the fluid elements is rotating. That flow then becomes an irrotational flow. In contrast, if the product of delta times V or the vorticity is not zero, then we say that fluid elements are rotating, and therefore we have a rotational flow. This is what rotational, irrotational means. From the name, it's probably obvious, but in terms of more fundamental things, is in terms of vorticity, whether it's zero or not. So, if vorticity is zero, it also means that this sum of velocity gradients is obviously zero. Okay, you can use that to say it's zero. Now, how does that lead us to from these concepts? How do we go to potential flow? Well, potential flow is just a name for a flow which is both inviscid, i.e., viscosity is zero, but now is also irrotational, where vorticity is zero. Is everyone clear? So you got two things there, very important. No viscous effects, and vorticity is zero. You combine these two, gives you something just to remember as a potential flow. So obviously, clearly, potential flow is an extreme simplification of real life. Okay, we're ignoring rotation of the fluid elements, we're ignoring the viscosity. Okay, and there are, you can add other simplification as incompressible, for example. So that's why potential flow is the simplest flow you can have in fluid mechanics. So I spoke before some of the characteristics of fluid elements. So fluid elements, when they are moving, they can do a number of things. So they can translate, that's just linear motion. They can dilate, that's basically the change in density. So if you take a small volume of fluid, sometimes under certain condition, it can actually change its density, as you can see here by showing bigger box. It can rotate at an angle, okay? And the reason I'm putting this in red is this is what we're concerned with when we talk about potential flow, whether, it's irrotational. So the rotation for potential flow is zero. But also, as you know, we spoke about shear stress last year in fluids. Fluid elements also have shear, all right? So all of these effects are things that exist. The main thing we're thinking about, at least for now, is whether there is rotation or not. So this is just showing you the definition of vorticity again, and its definition in terms of delta. So we can ask the question, is the concept of potential flow of any use to aerodynamicists, or to you guys, if you want to be an aerodynamicist, okay, or an aerospace engineer? The answer is yes. So if someone gives you this picture, which I think it's in the CFD lab as well, sorry, repeating, we can say, how would you model the flow going around such a complex vehicle? Okay? You can do an experiment in a wind tunnel, which is obviously very expensive, time consuming. You can do theoretical work, very difficult, very challenging, quite limited anyway. You may not even get a solution, to be honest. So nowadays, there's something called CFD. That's what you're doing in the labs. CFD itself, you'll be pleased to know, has different levels. The ones you're doing in your labs is actually quite involved. It's not simplified. It's actually, it has a lot of things in it, things like viscosity and so forth. On a lower level, from the complete CFD, if you like, there is something, this potential flow, which makes all these assumptions of irrotational flow and inviscid flow. Okay, they make our life easy. But then, how is that relevant to real life? Well, the answer to that is to say the following. Now, if we consider the flow around this aircraft, for example, if, as long as you are away from the body of the aircraft, what you guys will find is that the effects of viscosity are actually not important, and the fluid elements may not be rotating. So straight away, you can say, oh, I can actually make the approximation of a potential flow away from the solid boundary of the aircraft, and you can actually get a nice solution, quite reasonably accurate, actually. All right? But then you have the problem. What about the flow very close to the body of the aircraft? Well, you can add, there are methods where you can take effect of the boundary layer effects. due to viscosity, of course, but that's another matter. But the idea being, you can actually solve the outside flow using potential flow model, which is simplified and not difficult to do. Then somehow, assuming you know how to do the boundary layer, you can add the effects of viscosity, and then you add the solutions together, and then you have a solution, okay? Which is actually quite reasonable. So this is actually one way where potential flow is obviously very useful to do, is basically modeling the external flow over an aerospace vehicle. Now, this looks quite, this is actually Sean's love, because he did his PhD on that. So Sean did a lot of work doing his PhD on experimental flows around slender bodies, things that look like could be a missile or something. And you guys can see this is a pretty complex picture. So you've got a lot of vortices coming from different places, from the nose, from the canards, from the side body, and so forth. Okay, if you have control surfaces as well. So it's a pretty involved picture. The good news, however, even with that, it's actually quite common still to model these slender bodies using potential flow model, which is amazing. Despite all the assumptions we've made about the potential model being very simple, it's actually quite powerful in solving, giving us a good answer, not the perfect answer, but a good answer for this type of flows. Even though they have vortices coming through and complex flow pictures like these, but you can actually model that using potential flow. Now, I don't want you to get very confused by this picture. I'm just putting it for information to tell you the following. Now, in terms of complexity of the computational models you can use to solve an aerodynamic flow, you can roughly have the following picture here. So, we're starting with potential flow. We have right at the bottom here, right? This is like the simplest model you can start with. Then what people with time have done, you guys can see, start in the 60s, but now, of course, we have more things up in the at the top. But anyway, so people started adding more and more things into their models. Okay, until now we have what we call the Navier-Stokes at the very top. This is basically what you guys are doing in your CFD lab, is solving the Navier-Stokes, which is the full equation for solving a fluid flow. What we're doing so far is just a very simplified model at the very bottom. That's all I want you to tell there. So. I've told you already that potential flows are useful for external flows, very useful for slender body flows. We will see later when we talk about airfoil theory, we can actually use this potential flow model to give us an equation for how the lift is generated. So you will get an equation for lift, okay, and which you can use to calculate the lift from it, which is fantastic. Now, this is very important here, point number 4. Now, the beauty of potential flow is that you can combine a number of potential flow solutions to make something more complicated, like the flow over an aircraft. Although I told you can solve it, but the real thing is that you can add different simpler solutions together. So what we call superimpose mathematically. Okay, so you start with a very simple solution like a uniform flow, then you add a vortex to it maybe, and then you add together, you get different flow. You add something else until you make a complex enough solution for your problem. So that's the beauty of it. You can add solutions together to make something more complex. So out of simple things, you make something complicated. And actually, people still use it, believe it or not, nowadays. Even big names in Boeing and the rest of it, they still use a lot of potential flow methods and panel codes and the rest of it. And over the years, of course, you would expect they have developed a lot of codes. So whether it's commercial or military, so we've got, for example, the DATCOM, that's a code. Missile DATCOM, of course, for missiles. This one here, Trinair, is actually a Boeing code and was developed many, many years ago, but still, every time they develop it more. Java foil, yes, you all used it last year, except the pilot studies, sorry. And X-foil, some of you used it. So X-foil and Java foil are based on potential flow model, right? They're not very good in dealing with boundary layers, but they're okay. Well, they're adding things to it all the time, but really they're potential flow models. Okay, right. Now, potential flows, as I told you in that pyramid picture, if you remember it, is basically a subset of the full equations of flow, which are the Navier-Stokes. So you just imagine fluid flow is governed by a set of equations. They're very complicated, to be honest. You don't need to know them by now. I'm just telling you, the Navier-Stokes, they take everything into account: viscosity, rotation, dilation. They are fully compressible, everything. All those characteristics of flow I told you about at the beginning. These are the Navier-Stokes. Now, of course, you can go and solve the equations with no assumptions. That's fine. You get an accurate result, but computationally they're very expensive. But also, to solve them using numerical methods, they're not easy. So it makes sense. People made simplifications to make the solution of those equations easier and easier. One subset of that with certain assumptions is what we call the Euler Equations. So in Euler Equations, which is simplification of Navier-Stokes, we are saying no viscosity and no thermal conductivity. Okay. In potential equation, which is even simpler than the Euler Equations, we have no viscosity, no thermal conductivity. It's totally isentropic and irrotational. We spoke about viscosity and irrotational already. Okay, so you can see potential flow is basically a subset of the full equations, much simplified. So what do we do in potential flow? How do we get the model? What are the concepts related to potential flow? Well, it all starts, or it can start, with defining what we call a velocity potential phi. Okay, so this is a mathematical equation called velocity potential. But the good thing about it, it's not just something out of the blue. It's something that could be related to the velocity field V. So if you guys start with this velocity field V, which has components U, V, W in 3D, what we say is in potential flow theory, we can link that velocity field to a function called the velocity potential, which is actually a scalar function. Okay, it's not a vector quantity, it's a scalar function. And we can relate the two. The first thing is that this scalar function, called the velocity potential, is both a function of space and time. The key thing here is the following definitions, all right? The velocity field, I probably should have put capital V here, sorry. So that should be V, U, V, W. So these are the components. So the V is delta of phi. So it's the gradient of phi. So if you've done maths, what's the gradient of a function? You can calculate it. So we have this velocity potential, and out of it we can get the velocity field, which we then give us the pressure and give us the forces, okay? So that's how it is. This is the key idea here. Now, in terms of individual components, what you will find is that the x component of velocity u is actually d phi dx, v is d phi dy, and w is d phi dz. Obviously, if we just go to 2D, we can ignore the w component and we only deal with these two components. Okay? But that's very simple. I think it's quite easy to remember as well. So u is d phi dx, v is d phi dy, w is d phi dz. This is the main thing. So it's a scalar function, so only depends on location and time, this scalar function phi. But it's very important that it depends also on time. So, okay, so and time is important, of course. So it's a function of time. And just to remind you, this is just a reminder for the equation or definition of the delta operator, also known as the nabla or the del. Does it have any other name? What do you guys call it in maths as well, the delta? I think that's all the main names, the nabla, the delta. Okay, anyway, that's the definition, okay? And all you need to do there, just put phi. So d phi dx is u, d phi dy is v, and d phi dz is w, the velocity components. That's it. So which is fantastic. Right, there is another function I will introduce to you. It's called the stream function, and I'll show you how the velocity potential and the stream function relate. Maybe I do appreciate, maybe it's difficult now to imagine what is velocity potential. It's difficult. We know it relates to the velocity field, but let's maybe introduce as well the stream function. Before that, how are we doing on time? I didn't bring my... What's the time? 2? Quarter past. So we have 15 minutes, okay. Right, stream function and streamlines. All right, so let me show you the picture of the streamline again, okay? So it's very simple. Velocity is tangent everywhere, and the equation of a line is y equal fx, right? And if you guys remember, I told you you integrate this equation of the streamline differential equation to get fx of y equal a constant, right? That's the equation of a line. So that's all given, fine. Let's introduce this concept of stream function. So this function here, fx of y, we can actually denote it by something else, which is psi, okay? So we say this function fx of y, we give it the symbol, or can be expressed in terms of another function, psi x of y, which also we call a stream function, because it's related to the streamline, okay? Streamline, stream function. So therefore, instead of writing this equation, okay, fx of y equal to a constant, which is the equation of the streamline, we can actually now express the equation of streamline in terms of this new stream function, psi. So it just becomes psi x of y equal to c. So immediately now, you guys can define your streamline in two ways. Either by the differential equation, dy dx equal v over u, velocity components, or in terms of this new thing, the stream function, where the stream function along the streamline is a constant. That's the main thing, okay? How do you define a streamline? You just say, along the streamline, the stream function is constant, all right? And for different streamlines, we will have different stream functions and different constants, okay? So for one streamline, psi x of y equals c1, another streamline, psi x y equals c2, and so forth. So you have different streamlines, different stream function. Is everyone clear? Hopefully. So that's the concept of stream function. Right. But there is actually a nice physical interpretation to the stream function as well, it turns out, which always helps to keep track of all these concepts. So let's imagine, I'm sure you've seen this, something like this before, flow around an airfoil. All those lines are streamlines, okay? Anyone remind us what this point here is? Here? If you can see the mouse, what's this point here? Starts with S. Stagnation point, very good, yeah. What's the value of CP? That was in the exam. Equal 0? No, 1, yes. So CP is 1. Anyway, I'd like to test you anyway. So, streamlines. Okay, so let's say we have, all these are streamlines. So as I told you, each streamline can be expressed as psi xy equal to a constant c. Okay, so all those lines have their own size. So let's just consider these two lines on above each other. So the first one has psi1, a function of x, y, of course, equal to value c, a constant, and we just call that reference c. If we go to the next line, it will be described by a different stream function, psi2, and we can relate, the good thing is, we can relate the value of psi2 to psi1. So we can write psi2 is c reference plus a change in psi between the first streamline and the next streamline. So basically, this difference, of course, is phi2 minus phi1. And it turns out that the difference in stream function values between two streamlines above each other is equal to the flow rate between the lines. So if you know what the flow rate between two streamlines, okay, which is basically the volume flow rate, how much volume per second, I have to say, I didn't explain, that's actually V dot. So V is a volume, dot is the time, so it's how much volume per second, okay? So that's equal to the difference in streamline between psi1 and psi2. And that's a nice thing to remember. So the difference in stream functions of two streamlines is equal to the amount of volume per unit time between them. It's a nice thing to remember. All right. Here is another one, which is very important definition. So remember, guys, I told you that the velocity potential, phi, we related it to the velocity components u and v. Similarly, we can actually relate the velocity components u and v to the stream function psi. And it's in this way. So the velocity component u in the x direction is the partial derivative of psi with respect to y, whereas the v is minus the partial derivative of the stream function with respect to x. So please note the signs. And the reason I'm saying that, if we go one slide before, oops, sorry, you guys will see in terms of phi, the velocity potential is slightly different. It's not the same. So this is in terms of the velocity potential, the velocity components u and v. Here, they're quite different. So please note the sign so that you don't get confused. But the beauty of it, within potential flow theory, the velocity components can be related straight away to either the stream function psi on the slide or the velocity potential phi, which is fantastic because it's always, all aerodynamics really, if you know the velocity field, you will know everything. So that's the beauty of it. So just to remind you, in terms of the velocity potential phi, these are the velocity components. Please again note the sign. Right. So, what is the relationship between the velocity potential phi and the stream function psi? It turns out rather nicely that they are actually related. They're not cousins, but they are related. It turns out they are actually orthogonal functions. So, if I draw streamlines, phi 1, phi 2, phi 3, like that. Sorry, streamlines is, I was talking about the stream function, sorry. If I draw velocity potential lines, phi 1, phi 2, phi 3, and I have the stream functions, psi 1, psi 2, psi 3, and they will be orthogonal where they cross. So at every point they cross, they are orthogonal to each other, 90 degrees. Okay? So you can see that on this picture here or this picture here. And please remember, along a streamline, psi is constant, only psi, not phi. The other thing to remember is that the velocity potential, if you're still not confused, the velocity potential only exists in irrotational flow. But stream function, as long as you have a streamline, there will be a stream function. Doesn't matter whether the flow is irrotational or not. Whereas the velocity potential only exists if the flow is irrotational. Is everyone clear about that? Yeah? So stream function psi is more generalized than the velocity potential phi. Phi only exists in the rotational flows. Stream function exists all the time because it's always related to stream lines. So there is always a stream function, but not always a velocity potential, only if it's rotational. The other thing we can do, but we won't do, which is good news, is that we can actually create complex potential form of the flow using phi and psi as the kind of, they become the x and y of this new of this new potential w. So you take phi as the kind of the real part and psi as the imaginary part. So you can also make complex flows out of phi and psi. But again, we're not getting into that. So that's just for information. But the key point here is, please remember this property about velocity potential. Right. So let's look at other interesting properties about the velocity potential phi and the stream function psi. It turns out that they both satisfy the Laplace equation. So the Laplace equation is obviously written in terms of delta squared, the double delta basically, of a function equal to 0. So there is an equation called the continuity equation, which is basically the conservation of mass. Remember, there are three main physical laws in physics, and fluid mechanics is part of physics. So conservation of mass means mass is conserved. You can't create mass or destroy it. The momentum is conserved. That's basically Newton's second law. And finally, any guesses? What's the other?
Is it the energy law?
Well done, mate. Yeah, as the energy is conserved, you know, you can't destroy energy as such, but you can change its form. So these three principles are the cornerstones of all physics, including fluid mechanics, of course. So if we take the conservation of mass, which also known as the continuity equation, and express it mathematically for this potential flow model, we can write it as this. du dx, remember u is the velocity component in the x direction, plus dv dy, plus dv dx. I'm not sure if this is correct. That should be y, sorry, dv dy, equal to 0. Okay? Now, I've told you already that I can express u and v in terms of phi. So if I just go back and show you that u and v are themselves functions of y. So all I'm going to do in that equation now, substitute for u and v with d phi dx and d phi dy. So if we do that here, again that should be y. If we do that, we get the Laplace operator on phi, and what you will actually get 0. So what we're saying there is the velocity potential phi satisfies the Laplace equation, okay? Because delta squared of phi turns out to be 0. The same with the stream function. So if we take this definition here, anyone remembers what this definition is? We took it a few slides before. What's this? What's this property? Huh? Vorticity. Well done, mate. That's vorticity, and because it's irrotational, it's equal to 0, isn't it? That's the potential flow model. So this is vorticity equal to 0 in this model. Now, what we're going to do is substitute for v and u in terms of psi, okay? And of course, you've got the double partial derivative, which in terms of delta operator, basically the delta squared of phi, of psi, and you can arrange it this way, minus this term here, and you'll find it's actually equal to 0. Okay? So basically, both phi and psi satisfy the Laplace equation. What is so special about Laplace equation? First of all, the Laplace equation allows you to add solutions. Okay? So remember I told you at the beginning, in potential flow model, we can add solutions together to make a more complex solution. And this is mathematically because psi and phi satisfy the Laplace equation. Just think about it like harmonics. You know, if you hear a noise coming from a guitar or something, if you're in Glastonbury sometime, then that noise you hear is actually a series of harmonics, not just one harmonic. It's a series of harmonics added together to make that complex noise that you're enjoying. It's the same way with flows. If you model the flow around an aircraft, you can actually create that from simple flows together to make that complex picture. So it's kind of a series of harmonics added together. And the only way you can do that, because in this potential flow model, phi and psi satisfy the Laplace equation. So it's linear, we can add things together. That's the very important property of these functions. Right. I think I've said that already. They can be added together. Yeah, I've said this already. So, are we on time? Half past already? Okay, this is the last slide. There's no one waiting. No? I can do it. Right, so just to kind of think a little bit more about these equations, and just this slide is just to tell you again, all of what I've been talking about within the potential flow model is actually consistent within each other, and it kind of makes sense. So let's start with the continuity equation for incompressible flow. So this is the equation for continuity, mass conservation, du dx plus dv dy equal to 0. Right? If you combine that with the stream function, you end up with this equation, which satisfies Laplace's equation. All right? If you take the vorticity definition, and we know vorticity must be 0 in a potential flow, you combine it with the velocity potential, then you find that out of these two, you also get a Laplace equation. So they're all consistent. So velocity potential is consistent with vorticity, and continuity equation is consistent with the stream function. So it's all, they're all kind of complement each other and kind of make sense. Sorry, time runs out, but we will take an example next week, at least to have an idea, and more examples in the tutorial sheets.